We're going to cover chapter 4.2 through 4.3, and we're going to be talking about solution stoichiometry. Remember, stoichiometry was relating one chemical to another. Well, we relate one chemical to another through moles, and we have a new way to get into moles. So solution stoichiometry, and every time we get to a new way to get to moles, we'll have a new way to get to stoichiometry. We're going to talk about acid-base reactions, so we'll briefly go over what acids and bases are and look at some examples of acid-base reactions. We'll learn to balance some acid-metal hydroxide neutralization reactions. We'll just briefly go over the strengths of acids and bases and then get into acid-base stoichiometry, where if we know how much acid we reacted with a given base, we can determine how much base there was. And the technique in the lab that's used to come up with the data is called a titration. So we'll talk briefly about titrations as well. Okay, let's get warmed up with a little bit of review. And our first review question asks, what is the molarity when we have 60 grams of sodium hydroxide in 0.25 liters of solution? Well, we're using our units for this, and I can't think of any preliminary steps, so on to step one. Are we after big M bar? We've learned our lesson already. Big M bar looks like a single unit. No, we're after moles per liter. So make sure if you're after molarity that you set your equation equal to moles per liter. That makes sure that we start step two correctly, which is if we're after one unit over another, then we're starting with one unit over another. So we throw out our denominator line, and now we're going to ask between the 60 grams of sodium hydroxide and the 0.25 liters of solution, which of these goes on the top and takes us to moles of sodium hydroxide. And that would be the 60 grams of sodium hydroxide. That 0.25 liters goes on the bottom and will take us to liters, so that's actually our denominator's units already. Okay, let's take care of our numerator, so on to step 3, out of grams of sodium hydroxide. And I hope you found it easy getting this far. Now comes the big question, can we go straight from grams of sodium hydroxide to moles? We most certainly can. There's our most common calculation in all of chemistry, and we're done. Looking up the molar mass of sodium hydroxide, I have 23.0 for the sodium, 16.0 for the oxygen, 1.0 more for the hydrogen, for 40.0 grams per each mole. And when I put that on my calculator, I come up with 6.00 moles per liter. Do note our answer should have 3 significant figures. Next, we're told a sample of 50 milliliters of beer is found to contain 3.11 grams of ethanol. And there's the formula. Calculate the molarity of alcohol in this beer. Okay, again, we're using our units. Again, I can't think of any preliminary steps, so on to step 1. We're after the molarity, so big M bar. No, we learned our lesson. Moles per liter. Moles of the ethanol per liter of the beer. Okay, then for step 2, let's see, milliliters of beer, I think that goes in the bottom. Grams of ethanol, yep, that goes on the top. If you ever get stuck with the numerator's units, ask about the denominator's units. And now, on to step 3, let's get out of grams of ethanol. And here comes the big question. Can we go straight from grams of ethanol to moles of ethanol? We most certainly can. Alright, there's our numerator's units. Let's take care of our denominator. So out of milliliters of solution, can we go straight to liters? That's a simple metric conversion. And I hope that the metric system is simple for you. Okay, the molar mass of ethanol, we see the formula there, so 2 times 12.0 plus 5 times 1.0 plus 16.0 and another 1.0 for 46.0 grams per each mole. And then 1 milliliter, 10 to the negative third liter, base 10 number still going with the base unit. So 3.11, divide 50, divide 46, divide 10 to the negative 3, and I come up with a 1.35 molar solution. Now, what volume of 1.5 molar HCl solution is needed to provide 6 moles of HCl? Okay, we've got a calculation before us, equations or units, and we're still using our units. That's a good thing. Any preliminary steps? Let's pull out that conversion factor. That 1.5 big M bar really means 1.5 moles of HCl per liter of solution. In step 2, we know we're not starting with that 1.5 big M bar because it's not a single unit. Only the 6 moles of HCl is a single unit. So remember, that's why we do step 1 first. If we know we're after a number with a single unit, then we're going to start with a number with a single unit. If we're after a number with 2 units, then we would start with 2 units. Okay, on to step 3, out of moles of HCl. Can we go straight to liters of solution? And it's nice having that conversion factor sitting right there in front of us to tell us the answer is yes. And it also makes it clear where the numbers go. And I come up with a 4.0 liter solution. Only 2 significant figures. And now, how many grams of potassium chloride would you need to prepare 0.250 liters of a 2.00 molar solution? Okay, again, we would begin by asking, we've got a calculation before us, equations or units. Why do I do this? Because if you go to the beginning, it's always the same from the beginning. When it comes to a calculation, you only have one of 2 possible tools, equations or units, and in this case, it's units. Any preliminary steps? Now let's pull out that conversion factor. I'm going to do it the lazy way by extending the line and putting it over liters. Then step 1, we're after grams of potassium chloride. And step 2, we're going to start with that 0.250 liters of solution. We just made it clear that 2.00 big M bar is really 2 units. And now step 3, out of liters of solution. Now comes the big question, can we go straight from liters of solution to grams of potassium chloride? No, it's time to go into moles of potassium chloride using that concentration term that we're given. And then from moles of potassium chloride, we can go to grams. That's 2.00 moles of potassium chloride per each liter of solution. Then we look up the molar mass of potassium, add it to the molar mass of chlorine for 74.55 grams per each mole, for 37.3 grams of potassium chloride. What type of electrolyte is represented by the following equation? Well, the first thing we do is we look to see, are there ions? And there are. So to tell if it's strong or weak, we then look at the arrow, and the reversible arrow tells us weak. That reversible arrow means a limited amount of ions. Okay, and here we don't see any ions, so it doesn't matter what arrow we have. This would be non. Again, I see ions. So that's where I begin. Are there ions or not? And there are. Then the big arrow says strong. So again, first start with, are there ions? And then go to the arrow. And what type of electrolytes do we have here? Sodium chloride, a soluble salt. Well, soluble means we're going to get quite a bit to dissolve, so lots of ions, strong. Phosphoric acid, a weak acid. You may recall that weak acids formed low concentrations of ions and were weak electrolytes. Hydrobromic acid is a strong acid, and strong acids were examples of strong electrolytes. And for barium sulfate, we're not given any information. So we know this is a salt, an ionic compound, so we go to look at our table to tell if this is a soluble salt or an insoluble salt. And we see that it is shaded. The box for barium sulfate is shaded, meaning that this is an insoluble compound, so this would be a weak electrolyte. We're going to get some ions, but not a whole lot. And now we're asked to write net ionic equations when solutions of iron 3 nitrate and potassium hydroxide are mixed. Okay, well, first, in a solution of iron 3 nitrate, we have separate iron 3 ions and nitrate ions. Then, in a solution of potassium hydroxide, we have separate potassium ions and hydroxide ions. So there's step one, write the formulas of the participants. Then, step two, we're going to write the formulas of the products. And first we're going to find, are there any insoluble precipitates? We know the iron is soluble with nitrate. Is it soluble with hydroxide? And no, the iron 3 ion is not soluble with hydroxide and forms the insoluble precipitate iron 3 hydroxide. Okay, let's do the same thing for potassium. We know potassium is soluble with hydroxide. Is it soluble with nitrate? And I hope you recall that potassium, as all group 1A cations and nitrate, are always soluble with everybody. So that means that they remain unchanged. And now if they're unchanged, they are eliminated. These are our spectator ions. I'm going to go ahead and rewrite the equation and then balance it. Okay, I see one iron on the left, one on the right. The least common multiple is 1. Remember, how many your least common multiple is, that's how many you want on both sides. Then hydroxide, 1 on the left, 3 on the right. 3 is our least common multiple, so 3 hydroxides on both sides. Again, whatever your least common multiple is, that's how many you put on both sides. Okay, it's balanced by iron and hydroxide. What about by charge? So that +3 and -3, it gives you 0 on the left, the balance is 0 on the right. Sometimes we don't have charge balance. We need to remember to check for that. Okay, let's write another net ionic equation when solutions of magnesium chloride and sodium phosphate are mixed. Once again, step one, we write the formulas of the major species in each solution, and in magnesium chloride we have separate magnesium ions and chloride ions. In sodium phosphate we have sodium ions and phosphate ions. There's step one, write the formulas of the major participants. So for example, if they weren't soluble, then we would show the formula of the ionic solid. But that's not to be expected as reactants. We do expect them as the products though. Alright, so let's check our table. We know magnesium is soluble with chloride. How about with phosphate? And no, magnesium and phosphate form an insoluble precipitate, and so it's going to fall out of solution. Then sodium is soluble with phosphate. Is it soluble with chloride? Yes, sodium, as all group 1A cations, are soluble with everybody, including chloride. That means they remain unchanged, which means that the sodium ions and the chloride ions are spectators, and hence they're eliminated. Once we've eliminated the spectators, we're going to rewrite the equation and balance it. 1 magnesium on the left, 3 on the right. The least common multiple is 3. So 3 magnesiums go on both sides. Then 1 phosphate on the left, 2 on the right. 2 is our least common multiple. There's 2 phosphates on both sides. Now let me double check that it's balanced for charge. I see 6 positives and 6 negatives for 0 charge on the left to balance the 0 charge on the right. Okay, on to solution stoichiometry, and remember stoichiometry is the relationship of one chemical to another, and ultimately what that means is moles, mole ratios. Elements relate to each other through mole ratios equivalent to the coefficients in the balance equation. Every time we have a new way to get to moles, we have a new way to enter into stoichiometric problems. So we just saw through molarity we have a new way to get to moles. And again, every time we have a new way to get to moles, so for example in the chapter on the gas laws we'll have a new way, to get into stoichiometric calculations. Okay, as an example of a solution stoichiometric problem, we're told to use the net ionic equation where the lead-2 ion and 2 hydroxide ions forms lead-2 hydroxide. And we're asked what volume of a solution of 0.22 molar lead-2 nitrate is required to form 10 grams of solid lead-2 hydroxide. Okay, we've got a calculation before us, equations or units, and it's our units. Any preliminary steps? Yeah, let's identify that big M bar for the conversion factor it really is. Then, on to step 1, we're after the volume of solution. I'm going to put milliliters. Step 2, now we can see only one number has a single unit, and that's the 10 grams of the lead 2 hydroxide. And on to the beginning of step 3, out of grams of lead 2 hydroxide. And now comes the big question. Can we go straight from grams of lead 2 hydroxide to milliliters of solution, which by the way is milliliters of lead 2 nitrate solution? No. And where do we need to go first? Well, we know we're relating one chemical, the lead 2 hydroxide, to another chemical, the lead 2 nitrate. There's only one way to relate one chemical to another, and that's through moles. So first into moles of lead 2 hydroxide. And then from moles of lead 2 hydroxide, we can go into moles of the chemical we're after, the lead 2 nitrate. And now from moles of lead 2 nitrate, can I go to milliliters of solution? No, but I can go to liters. And then all that's left is to do a simple metric conversion from liters to milliliters. Okay, let me add the mass of 1 lead to 2 oxygens and 2 hydrogens, and I come up with 241.2 grams per each mole. The balance equation says 1 lead 2 ion, meaning 1 lead 2 nitrate, to 1 lead 2 hydroxide, and that's 0.225 moles of lead 2 nitrate per each liter of solution. And 1 milliliter, 10 to the negative 3 liters. You take that 10, divide 241.2, divide the 0.225, divide 10 to the negative 3. And when I come up with the answer of 184 milliliters and ask myself, does this answer seem reasonable? I'm going to say, yes, it does seem reasonable. It does make sense. Remember, we need to be asking that question, does our answer make sense? So what answer wouldn't have made sense? How about less than 1 milliliter? That really would not have made sense at all. Or millions of milliliters. That also wouldn't have made sense. We're not going to catch those simple mistakes if we don't ask, does our answer make sense? And you should be doing that with every answer you come up with. Okay, next we're asked to calculate the mass of the precipitate formed when 100 milliliters of 0.25 molar sodium hydroxide and 75 milliliters of 0.175 molar chromium 2 nitrate are mixed. Okay, well we have a couple of things going on here. One is we're given 2 chemicals, and so we have a limiting reactant problem. And then we have the mass of the precipitate formed. We have a net ionic equation that we need to put together as well. So let's start there. Let's put together the net ionic equation. And the sodium hydroxide is producing hydroxide ions. The chromium 2 nitrate is producing chromium 2 ions. And when we look up the solubility of the chromium 2 with the hydroxide, we find that's going to form an insoluble precipitate. Sodium ions and the nitrate ions are going to be soluble with everybody. Okay, so there's our net ionic equation, and now on to identifying that each of those big M bars are conversion factors. So let's identify the tools in front of us. Alright, well there's our preliminary steps behind us. On to step 1, we're after the mass of the precipitate, so the mass of chromium 2 hydroxide. And let's see, we're going to start with, again, this is a limiting reactant problem, so we're going to take the amount of each chemical and get the number of moles of product from each. And then the smallest amount is the max we can form. Okay, so taking that 100 milliliters of sodium hydroxide, we first go to liters. And then from liters, using the given concentration term, we go to moles of the sodium hydroxide. And now from moles of sodium hydroxide, we can go to our desired moles of chromium 2 hydroxide. Note we quickly went into moles because we knew the only way to get from one chemical to another is through moles. 1 milliliter, 10 to the negative third liters, and do note that's 0.250 moles of sodium hydroxide per liter. And then we see 2 sodium hydroxides, that's the source of hydroxide, per each 1 mole of chromium 2 hydroxide. For a 0.0125 moles of chromium 2 hydroxide. Okay, that's how much we can form from the sodium hydroxide. We're now going to do the same thing for the information on the chromium. Step 1, we're after moles of chromium 2 hydroxide. Step 2, we're going to start with that volume, the 75 milliliters of the chromium nitrate solution. And then step 3, let's get out of that initial unit, out of milliliters of chromium 2 nitrate. And yep, we're going to go to liters. How do we know that? Because we need to go to moles, and we're going to get to moles from liters. If I went back to the beginning, I would begin by asking, can I go straight from milliliters of chromium 2 nitrate to moles of chromium hydroxide, and realize the only way I can go through one chemical, chromium 2 nitrate, to moles of another, chromium 2 hydroxide, is through moles. How do I get to moles of chromium 2 nitrate? From that molarity. So first into liters and then into moles. Pretty much like we did above. Then from moles of chromium 2 nitrate, can we go to moles of chromium 2 hydroxide? Yes, we surely can. And our setup is complete. Again, 1 milliliter is 10 to the negative third liters. This time the concentration of the chromium 2 nitrate is 0.175 moles per liter. And it's a 1-to-1 reaction. So 1 mole of the chromium 2 hydroxide per 1 mole of chromium 2 nitrate. And this gives me 0.0131 moles of chromium 2 hydroxide. Now, how much can I actually form? The smaller amount. Again, this is a limiting reactant problem. If you're giving 2 of the reactants, then this is a limiting reactant problem. We determine what is that maximum amount, and the maximum amount is the least amount. Okay, now to get the actual mass, we're using our units again, after grams of chromium 2 hydroxide. Then start with the just determined moles of chromium 2 hydroxide. And then from moles of chromium 2 hydroxide, 2 grams of chromium 2 hydroxide. Now we need the molar mass of the chromium 2 hydroxide, so 1 chromium, 2 oxygens, and 2 hydrogens, or 86.0 grams per each mole, or 1.08 grams of chromium 2 hydroxide. Okay, before we move on, let's stop and look at what we did here. We were given 2 reactants and asked about the precipitate form, so that was a clue that we had a net ionic equation. We put together the net ionic equation, and then, as preliminary steps, identify the conversion factors that those concentration terms gave us. And then, being a limiting reactant problem, we determined a potential number of moles of product that can be formed from each, and then the smallest amount was the max that we could form. So one last calculation to convert from moles to mass. Okay, on to acid-base reactions, and there are several definitions of acids and bases that we'll learn about. One is that acids produce hydrogen ions in water. We call these proton donors, and we're calling them protons because once you take an electron away from a hydrogen atom, then all you have left is the bare nucleus, that proton in the middle. And bases gain or bond with a hydrogen ion. Simply, these are proton acceptors. Let me use those two definitions. I'm going to be latching on to those two definitions. Acids are proton donors, bases are proton acceptors, and now do note, each is the opposite of each other. And if one is donating protons and the other is accepting, that tells us that they're going to react with each other as well. Let's look at an example with a hydrochloric acid solution, that's at HCl. And we're going to react it with potassium hydroxide solution, that's the KOH. This isn't written as a net ionic equation, but we see the acid HCl, the base KOH. Actually, it's the hydroxide that's a proton acceptor. And it forms water and the salt potassium chloride. So the hydrogen ion and the hydroxide ion got together to form the water. That's how acids and bases neutralize each other. We characterize acids by the hydrogen ion. We characterize bases by the formation of hydroxide ions in solution, and together they formed water, and so essentially they neutralized each other. And then the counter ions formed that salt. We're going to find that in an acid-base reaction where you have a metal hydroxide and an acid reacting, that we're always going to form water and a salt. And I hope that we'll always remember that acids and bases react to neutralize each other. And while we're here, I'll point one other thing out, and that is we don't have acid reactions and we don't have base reactions, we have acid-base reactions. For somebody to donate a proton, somebody's got to be out there to accept it. For somebody to accept a proton, somebody's got to be out there to donate it. Okay, let's go over balancing acid hydroxide neutralization reactions, and ultimately to be a neutralization reaction, we have to have all of our hydrogen ions neutralized by all of our hydroxide ions, and those two numbers have to be the same. If I have an unequal number, then I have some leftover hydrogen ions or hydroxide ions. So we begin by making sure there is the same number of hydrogen ions as hydroxide ions. And by the way, that'll be the same number of waters that end up being formed. So let's look at this reaction where chromic acid is reacting with iron 3 hydroxide to form iron 3 chromate. We don't have the full formula, but that's what it's forming, and water. Now to balance this, we would look at the acid and how many hydrogen ions does it have? 2. And look at the base and how many hydroxide ions does it have? 3. Well, in order for them to balance each other, we're reaching for that least common multiple. And every time we hear that word balance in any respect, we're reaching for that least common multiple. We balance chemical formulas with the least common multiple. We balance chemical equations with the least common multiple. And now we're balancing the acids and bases with the least common multiple of the hydrogen ions and hydroxide ions. Okay, so the least common multiple of 2 and 3 is 6, which means we're going to have 6 hydrogen ions reacting with 6 hydroxide ions. 6 hydrogen ions means 3 of these chromic acids. 6 hydroxide ions means 2 iron 3 hydroxides. Let me rewrite that. And now, when it comes to the salt, there's always just one of them, and that really is a good thing because it makes it easy to do the rest of the math. How many irons must be in that salt? Well, I look on the left and I see there's 2 irons on the left, so there must be 2 of them. And how many chromates must be in that salt? Well, I look on the left and see there's 3 on the left, so there's 3 of them. And now we can see 1 salt counts for the 2 irons and the 3 chromates. And we already determined that 6 hydrogens got together with 6 hydroxides, and to neutralize each other they formed 6 waters. So the number of hydrogen ions, the number of hydroxide ions, and the number of waters formed will always be that same number, that least common multiple. Okay, let's do some more. Alright, we are asked to balance the following, and I see sulfuric acid reacting with sodium hydroxide to form sodium sulfate and water. Okay, sulfuric acid has two hydrogen ions. Sodium hydroxide has a single hydroxide. So the least common multiple of 2 and 1 is 2. So I need 1 sulfuric acid for 2 hydrogen ions, 2 sodium hydroxides for 2 hydroxide ions. And I'll get to the waters in a little bit. Okay, how many salts do we ever form? Just one of them. And how many sodiums must be in the salt? 2. And how many sulfates? 1. And how many waters were formed? 2. Now that we've done a couple, I'm going to invite you to balance this next one, where phosphorus acid is reacting with calcium hydroxide to form calcium phosphite and water. So you might want to pause until you're done. Okay, phosphorus acid has 3 hydrogen ions. Calcium hydroxide has 2 hydroxide ions. Since this number needs to be the same, the least common multiple of 3 and 2 is 6. For 6 hydrogen ions, we need 2 phosphorus acids. For 6 hydroxide ions, we need 3 calcium hydroxides. How many salts are we forming? Always 1. And how many calciums must it be accounting for? Well, I see 3 on the left. And how many phosphites? I see 2 on the left. And then how many waters were formed? That's 6. At least common multiple. 6 hydrogen ions got together with 6 hydroxide ions to form 6 waters. And I hope you were successful with this. And how about you do this one on your own as well? And in a few moments we'll join in and balance it together.